Okay. All right. So.
No, he said no. You have to point the mic.
I'm going to ignore that.
Pull the mic up more toward you.
All right. Is this better? Okay. So as you know, Elsevier is the largest science, technical, and medical publisher. We have a lot of content with us, across books and journals and things like that. Also, MD console, procedures console, and all that. But we have a big challenge, and it's not about getting the resolution of the monitor correct. The challenge is more in what do we do with the content, and it's about working with physicians. As a physician, I want to provide the best care for my patient. I can do that if I have the right information with me to make the best decisions. How do I do that? Now, as we've been listening to talk after talk yesterday, the problem that we are facing is that there's just too much information. We have doctors are faced with a barrage of data. How do we deal with this? Gone are those days when, if you're diagnosed with the disease, then your choice was between one or two alternatives. Now, we have a multitude of alternatives to deal with, and new procedures and medications are coming in every day. So how do we deal with this? And the problem is, okay, now even if we have the information, how do we find it, and how do we apply it in the context of a patient setting? So the challenge is that we are spending more time searching for information and less time actually reading it. And some folks say it's almost an 80-20 kind of a thing. 80% of the time we seem to be spending searching for it rather than reading it. Now, we broke it down into 3 areas. The information needs to be comprehensive, it needs to be trusted, and we need to be able to get the answer very, very quickly. So, I'm going to give you a look at what SmartContent is, how taxonomy is applied to enable this, and go over a couple of applications that we've developed on top of SmartContent. Clinical Key is one we just released, and Linked Data Repository is a platform that we're building. Okay, so when you look at content, published content, a lot of it is started off as unstructured content, whether it's books or periodicals, etc. It's primarily meant for human consumption. The next step in the evolution of this is structured content, where we introduced XML. So we start identifying pieces and parts of the content as, this is a table, this is an abstract, this is an image, kind of thing. The next step in this evolution is basically to be able to understand what the content is about. What is the content saying? What is this table contain? What is this image about? It's basically identifying this kind of fundamental information that is present within our content. And to do this, we identified the SmartContent as a core infrastructure to enable the building of applications which can take advantage of this understanding. So SmartContent is about basically understanding what we have, and then being able to, the products on top of it, can take advantage of that and, provide point of care information, provide, more accurate search results, faceted navigation, and from analytics, if you know what we have, then we're able to better identify what we can do with it. Personalization. Now, at the point of care, when we're seeing a patient, you want to know what information is applicable in that specific context, not in a generality, but for that patient, what is useful. So we want to be able to personalize that information. And then, as part of the editorial process, also we can apply tags and to better understand or better know the content. Okay, where does taxonomy fit into all this? So let's step back a little bit and see, what does taxonomy really mean? Wikipedia says it as it's basically a classification. It's a science of identifying, naming, and organizing things so that it makes sense. So looking at it on a scale, you start from a simple thing like lists, move up the complexity scale to control vocabularies, terminologies, and ontologies being the most expressive form of taxonomies. I'm going to show you what we do here in EMMET. Okay. EMMET is our Elsevier merged medical taxonomy. And we leverage the UMLS, which is the Unified Medical Language System. And it provides us with terms, definitions, and alternate names and all that nice stuff, so that we can understand that malignant neoplasm of the breast is also called as breast cancer. It's also called as malignant tumor of the breast. There's several names by which it is called, but it's still the same thing. It's one entity that we are talking about. We also have codes which link it to many different medical vocabularies like ICD-9, 10, MESH, SNOMED, CT, etc. And we also know that it is this basically is a type of disease that we are talking about. Okay. Now, being a terminology, we talk about hierarchies. So we know that malignant neoplasm of the breast is basically a breast disorder. Okay. Again, being hierarchy, we also can subclassify this. And we know that we have specializations of this like sarcoma or a lymphoma of the breast. And this is all the hierarchical relationships that we can get here. There are other types of relationships, and these are associative relationships. And these examples like, a breast cancer has symptoms like a breast lump or a nipple retraction. We have diagnostic procedures, medications, risk factors, and preventive steps that we can take. Okay, another look at this. A different example, we're looking at acromegaly. This is another condition where you have really large feet, hands, and the head can get enlarged. It's a form of gigantism, and it comes from a disorder of the pituitary gland or hypopituitarism. It's got a sub classification as renal biliary disease and Hagman. Now, this is as you can see on the right-hand bottom corner, it is a relationship we're talking about here. And is a relationship is saying that every instance of acromegaly is an instance of gigantism. Now, there are other relationships we can talk about here. Pituitary gland or hypopituitarism is a disorder of the pituitary gland. So it has an associative relationship to the pituitary. Now, the pituitary has two parts, a neurohypophysis and an adenohypophysis. And acromegaly is actually a disorder of the adenohypophysis. That's how we'll link these things together. Now, why do we get acromegaly? It's because the adenohypophysis secretes the growth hormone, and acromegaly is a disorder of increased secretion of the growth hormone. So we can represent these kinds of associative relationships as part of our terminology. More of this, acromegaly has findings. We can represent that formally. It has finding relationships, large jaw, large hands and feet. Other things like, how do we diagnose this? We can get a growth hormone level, which is about the growth hormone. We have an MRI of the head, which can detect a tumor in the pituitary. And then the treatments. We look at medical treatment. We look at, we have, the surgical procedures that are used to treat acromegaly. Now, coming back to the hierarchy here, we've seen that these two conditions are subclasses of acromegaly. So focusing on just this one, it also turns out that it is a disorder of the ovary. So what we have here is a situation, so in here we see a single parent. So it's a single hierarchy. But what we can also do is we can represent the other relationship to the ovary with another is a relationship. So this is an example of a polyhierarchy that we can represent in our terminology, and we can take advantage of this in the applications. Okay. So how do we do this? Like I said before, we leverage standard medical vocabularies, SNOMED, CT, ICD-9, etc. We also use other Elsevier in-house resources like Gold Standard, which is a pharmacology or a drug database, and some custom vocabularies that we're building. We have a dedicated team of full-time knowledge representation specialists working on this. They look through the search logs, they look through books, etc., to identify synonyms, to identify new terms that we want to add in there. So it's a constant process of improving that's going on here. Okay, and then we use this basically to understand the content of all these different types of contents: clinical trials, journals, guidelines, books, PubMed articles, etc. Now, since we this was from an earlier snapshot, now we have over 500,000 core clinical concepts, over 2 million synonyms, and other kinds of relationships. And here is a process that we use basically to taking the content, applying the taxonomy, and getting smart content out of it. So on the left side, you can see the types of content we have, and up there is the taxonomy. We normalize the content. Everything is in a standard format, and then we pass it through a query parser, and that identifies the text in the content and applies the tags to it. And the result of it is an index we get of all the annotations. It's not of the raw text, mind you, it's the annotations that are there, all the tags that we have identified in the text itself. Now, as a parallel process, we also do some raw text indexing. Okay, so that's the full text index, which complements the concept index that we have here. Now, that's all available in a searchable format now. From the front-end side, when a user types in a search term, the very same query parser engine reads that the term or the phrase and matches it to the terminology that is there. So now we're able to take a user-entered query and translate it into one of the terms in our model. Now, and then we use that to do the searching. So here is an example of the kind of things that we can do. Tricuspid regurgitation is a disorder of the heart. And when a user searches for this, we identify that it actually matches the concept, tricuspid valve insufficiency. Now, when there is a concept match, it receives the highest weightage, and we're able to very quickly find all the different ways in which tricuspid valve insufficiency is used. So we not only find words which say content which says tricuspid regurgitation, we also find which says tricuspid valve insufficiency. Slightly different example: aortic stenosis treatment. So here we have a concept match which is aortic stenosis, and we know that because of the semantic relationships we have, this is talking about treatment associated with aortic stenosis. So now we're doing a concept match and using the relationships that are available with the concept. Previously I gave you the example of acromegaly, which has those associative relationships. So we're able to leverage that and tailor the results to not only the phrase aortic stenosis treatment, but every single way it is used. If it says if an acronym is used, say AS, we can say AS treatment. That's identified as well. Now, the way we do this is by calculating different weightages to these concepts that are matched. Now, when a document is processed, depending upon the terms that are identified, we give different weightages. As you can see here, we are using BNP guided versus symptom guided heart failure therapy. So BNP is an acronym here. It stands for brain natriuretic peptide. And what we do is not only are we able to identify the exact acronym in the text, we are also able to identify the full form. Now, all of a sudden, where these terms are used very heavily, that document gets a much higher weightage here. So that provides us a way to better tailor the results to understand what this document is about and deliver the right kind of results to the user. Now, doing smart content or extracting or identifying smart content or turning content into smart content is an extremely complicated process. How do we know that we are doing it right? So our QA is a multi-pronged approach. So we have a technical test set where we are validating are the fields that we are identifying are they correct? Are we identifying the abstract sections? Are we identifying the treatment sections? So the document is divided into different sections. Right? So we are able to leverage some of those and identify, okay, are we applying different weightages to these different sections? So that's the technical part. We also have a goal set that has been manually tagged. So we take articles, documents, books, etc., and it's manually annotated by professional annotators, and that we used as a comparison for identifying, okay, is the automatic tagger and indexer working on identifying this correctly. We have a query set where we are testing the results. We compare the results from Google with our search results and see, okay, are we getting better results than that? We look through search logs to see what kind of terms what kind of keywords are being used by users, and are we able to identify them? Are we missing any of those? Those go back into the taxonomy, and to enhance them. And a lot of times it's like identifying labels or alternate ways in which people are using these concepts. Sometimes it's altogether new concepts. And then we have linguistic use cases specifically built so that we are able to test the use of the way language is used. Let me show you an example. Okay, we need to be able to identify that HIV1, HIV with the space 1, and HIV1, they're basically the same thing, right? It looks very, very simple. As a human being, we're able to parse this very easily, but for a computer, this is extremely hard stuff. So we need to build special cases to basically to provide for these kind of things and test it out. Now, here is another example: cytokine CXL6, and with a space, without a space. It's one concept. So we need to be able to identify the different forms in which this is used. Acronym WHO or W.H.O. It's the same thing. So there are other forms of this. You can have a hyphen, you can have slashes. We looked at the periods. So there are a number of different ways in which a concept or a term or a label is used, and we need to be able to identify in the text that they all mean the same thing. Okay. So that's all the background. Okay, it looks all the kind of the work, the infrastructure that we need to build to make to have real applications at work. So I'm going to show you two things. One is clinical key, and the other one is the LDR, Linked Data Repository. So on the clinical key side, this is a search and discovery application. Now, stepping back for a minute, doing deep semantics is really, really hard work. And as Bernadette and are going to tell you, it's not an easy task. But so we've taken a very incremental approach to this. So clinical key is our first application that we have built on top of SmartContent. It leverages our terminology, and it scales up to be able to deliver almost 2 terabytes of data in a fraction of a second. We have indexed almost 2 terabytes of data on all Elsevier healthcare content, along with publicly available content, to deliver this. So what you can see here is, as you're typing in the words, we are able to auto-suggest the matching concepts. Now this seems very simple because we're used to Google doing this all, so we expect this. Okay. Now what we do here is we are able to detect what the user is typing and match it with the core concept that we have in the terminology, and identify the list of possible matches along with the type of term that is, as you can see on the left side there, that this is a disease. Now, not only are we doing the auto-suggest with the type of disease, we are also able to use the relationships to say, okay, you can also look for these other things. So you're able to refine the kind of things that you want to look before you even start the searching itself, right? Maybe it's not about tricuspid regurgitation that we want to talk about. It's actually about a diagnostic procedures in a case of tricuspid regurgitation. So we're able to use a relationship to provide that level of auto-suggest. Okay. Furthermore, once you have the results, you can filter on the speciality. It takes into account the kind of terms that are there in the document, and you're able to filter broadly along the specialities. Now, along with the search results, on the right side, you can see where this has actually matched the text to the level of the paragraph. And now, this is a case of tricuspid regurgitation. The other ways in which this can be referred to is tricuspid insufficiency or tricuspid valve regurgitation, TR. So all these different forms can be identified and they will be highlighted. We're able to process the metadata associated with the images. So we can narrow down and say, okay, this is an image about tricuspid regurgitation. This is an echocardiography image of tricuspid regurgitation. All right, so that's a search and discovery application. Now, some of the other cool things that we are doing. Okay, now Bernadette is going to talk more about the linked data. So this is just a glimpse of the kinds of things that we are working on. So we started with Elsevier content. We have a knowledge organization system, and we are processing it into the text, tables, images, etc. And we've created a graph of all the information that is contained in that. Now, this is what I'm talking about here is not an index that we built for the search and discovery application. This is a slightly different form of that same information as an RDF graph. And now once we have this kind of an RDF representation, we are able to link to other data sources across the world which use that same representation. So linked open data, a number of very, very interesting data sets are available in the linked open data format. So we're able to link to that. And once we are able to link to it, not only are we providing just the Elsevier content there, we are able to integrate it with content from Europe or from a different organization in a very, very transparent manner. We're able to improve our search and discovery process with this. And along with this, we are also able to do some, because it's an RDF representation, we can use Sparkle and other technologies to do quite deep semantic queries. So on top of this LDR or linked data representation, we have, we can do some tag clouds, we can do heat maps, different forms of visualization of the data, which gives users an ability to slice and dice it the way they want. This is a small demo that we've done in the past. We're connecting linked open data on the pharmacogenomics area. So we've connected Elsevier content with the diseasome database, and we're able to do it very, very transparently. So thank you very much, and if you have any questions, I'm happy to.